carbonic acid bicarbonate buffer system. In the human body, it is for many fluids important to have pretty and exactly pH vector. And to keep it on one level, there's the carbonic acid bicarbonate buffer system. And it can work in both directions. Now, it can be done as a carbonic acid, that is then H2CO3, or as the bicarbonate ion as HCO3 minus. If there is too much H+, then the bicarbonate ion, the HCO3 minus, can take the H+. So if there is too much acid, then there are too much H+. If there are too much H+, that means there is too much acid. And the bicarbonate ion, the HCO3 minus, takes now the H+. Now we're having no longer the bicarbonate ion with HCO3 minus, but also the H+. So we're having H2CO3. HCO3 minus plus H2 equals H2CO3. The H+ was added, so we're having no longer HCO3, but we're having H2, 2H, the other H, HCO3 minus H2CO3, and the minus is gone because it was an H+. So if there was too much H+ to acidic solution, the bicarbonate ion HCO3 minus took the H+, added it to its formula, and it has it in it basically, and it is now just H2CO3. The other way around, there is a shortage of H+, so it's an alkaline solution, it doesn't have enough acid. Now this thing can split up. It is an H2CO3, and it just gives off its H2, its H+. Now it's no longer H2CO3, but just H. And then HCO3. And it's again the HCO3 minus, because it gives off again the H+, the plus. So it's no longer H2CO3, but it's now HCO3 minus. It lost an H, and also gets it minus because it has given off a plus. And the other, so the first thing was it was too much H+, so the normal bicarbonate ion, the HCO3 minus, took the H+ and became an H2CO3. And that can be split off in H2O and in CO2, so in water and carbon dioxide. Because it's H2CO3, that can be done in water into H2O. H2CO3 can be done into H2O, water and carbon dioxide, CO2. And the other way around, to little H2, H+, and the H2CO3 splits up into HCO3 minus. That is according to Gerard Tatorga and Stankovsky's Principles of Anatomy and Physiology book on the page 41 and 42. This is no medical advice. If you turn this video at one point away, close it, please tell me what the reason for it was so that I can improve. Otherwise, hi and welcome. I'm trying to learn biochemistry today, maintaining pH buffer systems, and after we've done that, we're going to do squat training. And if you participate in the squat training, then it's at your own risk. Maintaining pH buffer systems. Although the pH of body fluids may differ, the normal limits for the various fluids are generally quite narrow. Homeostatic mechanisms maintain the pH of blood between, so we're talking about internal anatomy and so on, of blood between 7.35 and 7.45, slightly more basic than pure water. Saliva is slightly acidic and semen is slightly basic. Because the kidneys help remove excess acid from the body, the urine can be quite acidic. Even though strong acids and bases are continually taken into and formed by the body, the pH of fluids inside and outside cells remains almost constant. One important reason is the presence of buffer systems, which function to convert strong acids or bases into weak acids or bases. Strong acids or bases ionize easily and contribute many H+ or OH- to a solution. Therefore, they can change pH drastically, which can disrupt the body's metabolism. Weak acids or bases do not ionize as much and contribute fewer H+ or OH-, hence they have less effect on the pH. The chemical compounds that can convert strong acids or bases into weak ones are called buffers. Now here comes the part important for us, but we're going to want to do a video about it. We read that already in previous parts. One important buffer system in the body is the carbonic acid bicarbonate buffer system. Because carbonic acid, H2CO3, can act as a weak acid, and the bicarbonate ion, HCO3-, can act as a weak base, this buffer system can compensate for either an excess or a shortage of H+. For example, if there is an excess of H+, so it is acidic, HCO3-, the bicarbonate ion, can function as a weak base and remove the excess H+ as follows. The bicarbonate ion HCO3- takes one of these too much excess H+, and now it forms carbonic acid, H2CO3. And that can be formed on, it's not explained here, to H2O and CO2. On the other hand, if there is a shortage of H+, so to little H+, an alkaline solution, H2CO3, the carbonic acid, can function as a weak acid and provide needed H+ as follows. So there is this H2CO3 available, this carbonic acid, and it can be split up into a hydrogen ion, the H+, which is now more, that there was a shortage of these H+, and also again the bicarbonate ion, the HCO3-. Now, we stumbled the last time because we couldn't find out what the name of HCO3- is. We're just going to explain it the way we do it here. We're just going to say the carbonic acid bicarbonate buffer system, that is the carbonic acid, H2CO3, and the bicarbonate ion, HCO3-. And you're going to explain, if there's too much H2, so too much acid, then the bicarbonate ion, HCO3- can take such an H+ and form together. Now it becomes H2CO3, and that can be formed on an H2O and CO3. And if there's too little H+, then such an H2CO3 can break up into NH+, and then the bicarbonate ion again HCO3-. I think I have it all. I may be just not completely sure about the things. It is carbonic acid and bicarbonate ion, H2CO3, HCO3-. The other things are a little bit hard. And it is called the carbonic acid bicarbonate buffer system. Acid bicarbonate buffer system. I'm going to stop the second camera and I try to save it. Carbonic acid bicarbonate system. In the human body, it is important that many things in the human body stay in pretty exactly pH factor. And that is, for example, happening with a carbonic acid bicarbonate buffer system. And that consists, basically, it can make usage of the carbonic acid, which is H2CO3, and the bicarbonate ion, which is HCO3-. Now, if there's too much H+, so too much acid, then there is too much H+. Then a bicarbonate ion can come, take that H+, so the bicarbonate ion, the HCO3-, takes the H+ and becomes H2CO3. So HCO3- becomes H2CO3. It's now 2H. It took that H, and that H was a plus, so the minus of the bicarbonate ion is away. So it was HCO3-, and it is now H2CO3. The H+ is now in it. And that can be then further made into just H2O and CO3. So H2CO3 can be made into H2O. H2CO3 can be done into H2O, which is water, H2O. 2 hydrogen, 1 oxygen. And it can be H2O and CO3, which is carbon dioxide, CO2. And the other way around, if there's too little H+, then the other thing, the carbonic acid, the H2CO3, can take such an H+, and then it becomes H2CO3. So there was an H2CO3, and it takes now that H2 and it becomes the H2CO3 minus. And then it has it in it. Let's look at that one thing again. H2CO3 is the carbonic acid, okay. And what becomes it? And no, that was it and it splits up, so I have it, that is why it doesn't work with the H2, we have it already. We have it and we split it up, so there we are. Carbonic acid bicarbonate buffer system. In the human body, this is for many fluids important to have pretty and exactly pH factor. And to keep it on one level, there is the carbonic acid bicarbonate buffer system. And it can work in both directions. Now it can be done as a carbonic acid, that is then H2CO3, or as a bicarbonate ion as HCO3 minus. If there is too much H+, then the bicarbonate ion, the HCO3 minus, can take the H+. So if there is too much acid, then there are too much H+. If there are too much H+, that means there is too much acid. And the bicarbonate ion, the HCO3 minus, takes now the H+. Now we're having no longer the bicarbonate ion with HCO3 minus, but also the H+. So we're having H2CO3. HCO3 minus plus H2 equals H2CO3. The H+ was added, so we're having no longer HCO3, but we're having H2, 2H with the other H, HCO3 minus H2CO3, and the minus is gone because it was an H+. So if there was too much H+ to acidic solution, the bicarbonate ion HCO3 minus took the H+, added it to its formula, and it has it in it basically, and it is now become just H2CO3. The other way around, there is a shortage of H+, so it's an alkaline solution, it doesn't have enough acid. Now this thing can split up. It is an H2CO3, and it just gives off its H2, its H+. Now it's no longer H2CO3, but just H. And then HCO3. And it's again the HCO3 minus now, because it gives off again the H+, the plus. So it's no longer H2CO3, but it's now HCO3 minus. It lost an H and also gets it minus because it has given off a plus. And the other, so the first thing was it was too much H+, so the normal bicarbonate ion, the HCO3 minus, took the H+ and became an H2CO3. And that can be split off in H2O and in CO2, so water and carbon dioxide. Because it's H2CO3, that can be done in water into H2O. H2CO3 can be done into H2O, water and carbon dioxide, CO2. And the other way around, to little H2, H+, and the H2CO3 splits up into HCO3 minus. That is according to Gerard Titor and Sen-Grabowski's Principles of Anatomy and Physiology book on the page 41 and 42. This is now medical advice. I'm not sure people understand. I don't know, maybe even shorter explaining. I don't know. I have to look at this. The first one was better. I'm going to stop the camera. And that was the biochemistry part. If you were here for biochemistry, you can come directly to the next part of biochemistry if you stay here and participate in the squat training. Then it's already on risk. We are bringing the leg up. And the other one. Take the leg at the ankle. Straight back, knee to the ground. And I'm still thinking about it. It's squat training. So we're going to the side. Let's just do it. The toes are pointing in front and we're stretching the inner side of the leg. And to the other side. Toes in front and stretch the other side. And go from side to side, the Mantis exercise. And in the left. And now squats, we're doing So legs wide apart and down to the first one. And the second one. Number 3 and 4. And if you're doing 2 more, we're having the half. 5 and 6. So that is the half. Let's go strong on into the second half. And this is 8, I think. And 9 and 10 and 11 and 12. And now the 6 back squat squeeze exercise. Down into quarter squat and press against the top of the leg only on one side. And on the other side. Down into half squat and press against the middle of the leg. And on the other side. Down into 3/4 squat and press close to the knee. And on the other side. And up again. And now the fastest giraffe of a water pond exercise. Down into 3/4 squat. Press against the leg. Go towards it. Then again, press. Go towards it again. Press. Go towards it. Press. Go towards it. Again. Go towards it. Press. Go towards it. Last 2. Press. Go towards it. And up. Last exercise. The propeller. Down into full squat. Arms to the side. Over to one side. Press against the leg. Look up to it. Middle. Over. Press against the leg. Look up to the head. Middle and up. And now a little stretching. Pull one leg up. The other leg. Heel into the ground, pull the toes in. Foot to the left, pull the toes in. To the right, pull the toes in. Middle, move the leg from left to right. Other heel into the ground, pull the toes in. Toes to the right, pull in. Left, middle, and move. And take the leg to the ankle. Upper one. Legs wide apart, breathing along. And up, out. Breathing in, close the legs, and breathing out. That was my squat training. Thank you very much.